Today we're going to work on section 7.4, which is arc length and surfaces of revolution. Arc length is like the arc length we worked with in trigonometry, and in trig we looked at finding the length along an edge of a circle, of just a portion of that circle, and we're going to look at doing the same thing with arc length here, but we're going to find a portion of the edge of a curve, so it doesn't necessarily have to be a circle. As you notice the equation here for a smooth curve from A to B, our arc length is actually an integration from A to B, and it's actually an integration of a square root of 1 plus the derivative squared. So the first thing we'll be working at when we do these problems is taking derivatives, and then we're going to add one to them, square them, add one to them in the square root, and integrate. So we have a lot of little steps involved here, a lot of algebra involved in these problems. Oh, and they can be defined in terms of x or of y, and so we can also have the same kind of a description in terms of y. Alright, so this first one we have an interval from 2 to 5, and we're supposed to find the arc length of this particular function. Just like I mentioned a moment ago, our function, we need to find the derivative of it. So let's first take a look at this particular function written in a slightly different way. Remember, this is actually 1/10 times x to the 5th. And likewise, we could write this as 1/6 times x to the negative 3rd. It's a little bit easier to see that as x to the negative 3rd to do our derivative. So I'm going to do the derivative y prime. And y prime would be that 1/10, and then the derivative of x to the 5th would be 5x to the 4th. And then we have the 1/6, and we have the x cubed, which would actually be negative 3x to the negative 4th. And then if we simplify, I end up with 1/2 x to the 4th, and then minus 1/2 x to the negative 2. And just because it's going to work a little, x to the negative 4, just because it's going to be able to work a little bit easier with it done this way, I'm going to go ahead and factor out the 1/2 from each of these, so I'm left with 1/2 times x to the 4th minus x to the negative 4th. And then we're ready to set up our integration. So our integration is going to go from 2 to 5, and it's going to be the integral of the square root of 1 plus, and then it's 1/2, and we have x to the 4th minus x to the negative 4th. All of that is squared, including the 1/2, and then dx. So as we're working with this particular piece, we want to take a look at how we go ahead and square that component of what we have. So I'm going to copy this and move this onto our other screen. Alright, so as I'm squaring this, of course, I'm able to square the 1/2 directly. But the other component of this, the x to the 4th and x to the negative 4th, I actually have to FOIL for that piece. So I've got 1 plus, and I have 1/4, and then I need x to the 4th minus x to the negative 2, and I need to square them. And I still said x to the negative 2, I'm sorry, it's x to the negative 4. Alright, let's get that in there written correctly. Alright, so when we FOIL this out, in fact, you know what, let me do that at this point too. We'll just write it down at this step. I need to do x to the 4th minus x to the negative 4th times itself. I actually end up getting, so this is the integral from 2 to 5, the square root, and this is 1 plus, I'm going to leave the 1/4 out here in front for the moment. The interesting thing is that when I multiply x to the 4th times x to the 4th, that x to the 8th. But the inside here terms and the outside terms are exactly the same, and x to the negative 4th times x to the 4th is actually x to the 0, which is 1. And I've got 1, or actually negative 1, both on the inside and the outside, so this is negative 2. And then plus the x to the negative 8th. And this is dx at the end. Alright, now I'm actually going to distribute that 4 through, but not exactly like you might expect. I'm going to write it as 1 plus, and I'm going to write the x to the 8th minus 2 plus x to the negative 8th over 4 as such. And notice we would need to get common denominators. And so this one would actually be 4 over 4. So if I were looking at this, I could also write this in such a way that I have the square root of x to the 8th minus 2 plus x to the negative 8th over the square root of 4, which is 2. So because I have this fact, I can actually pull that 2 out in front, and then of course it's in the denominator, so this is a 1/2 times your integral from 2 to 5. And I've got the square root of x to the 8th minus 2 plus x to the negative 8. Alright, so we'll move on to a new slide, and here's what we have. Alright, so taking a look at this, in order to work with what's here, I actually need to take what's underneath the denominator and I need to factor it. And if you'll notice, it actually factors, I forgot one piece, didn't I? I forgot actually combining over here the 4 with this negative 2, which gives me a positive 2. So my inside's actually got a positive 2 on there instead. So let's fix that. Alright, but it's an awful lot like the factoring I would have when I had negative 2. So I have x to the 4th, and I actually have the x to the negative 4th at the end, and I have x to the 4th at the beginning, and I have an x to the negative 4th at the end. And then inside I need addition, and I've got my integral from 2 to 5. So, of course, this is very handy because what I actually have here then is I have the square root of x to the 4th plus x to the negative 4th squared. And of course my square root and my squared are inverse operations, so they cancel, so I really have 1/2 the integral from 2 to 5 of x to the 4th plus x to the negative 4th dx. And we will integrate that. So again, my 1/2 out here in front. I have x to the 5th over 5. And then I have plus, and I have actually x to the negative 3, because I've added 1 over negative 3. And these are supposed to be evaluated from 5 to 2. So this isn't quite as nice as the interderivatives that we've been working with recently because we've had a lot of zeros involved, but it's still workable. So I have 1/2. I have 5 to the 5th over 5 plus 5 to the negative 3rd over negative 3. And then I have minus 2 to the 5th over 5 plus 2 to the negative 3rd over negative 3. If you plug that in your calculator and simplify, you'll either get the decimal, which is the exact decimal, 309.3195, or if you really want to write it as a fraction, you can write it as 618,639 over 2,000. Alright, so that's that one. We're going to take a look at number 2. Number 2 is a little bit more easy to work with just because of this keyword in the directions. It says find the arc length with the help of a graphing utility. What you will find very quickly in this particular problem is that we have to use a graphing utility to do the problem. So this is my arc length, which is s. It's equal to the integral from 1 to 3 of the square root of 1 plus, and this is supposed to be the derivative of what I've got here. So notice right here, right now, I actually have y equals x to the negative 1. So if I take my take my derivative, this is y equals, and it would be negative x to the negative 2. You can either leave it written like that, or you could change it back into fractional form. I'm going to go ahead and just leave it the way that it is for now. So this is negative x squared to the negative 2. Rather, let's get that negative in there. And all of that's supposed to be squared, and then dx. Alright, so we take a look at this particular problem, and we will simplify what we can in the inside. So this is 1, and it will be plus x to the negative 4th. And we'll run into a problem very quickly that in order to work with this, I would have to use u substitution, and then u substitution doesn't work because I don't have the derivative of x to the negative 4th on the outside of this. So my graphing utility will come in very handy. I can plug this into y1 in the calculator. So this goes into y1, and I can use function integration, which is under Math 9. I can tell it y1 of x between 1 and 3. And if I plug that in with 3 decimals of accuracy, I get 2.147. And we'll go ahead and use 3 decimals of accuracy unless your calculator, or unless the problem tells you otherwise. Alright, so we have one more topic to talk about in this section of material, and that is surfaces of revolution. And this has got a similar feel to it as the arc length, because you notice they've got a square root, and we've got the 1 plus the derivative squared. But you also notice on the outside, we've got that r of x, which kind of harkens us back to maybe the Shell's method, you know, a radius times a height times dx kind of a problem, and the 2 pi in front of it as well. And what we're going to be doing is we're going to be identifying the radius, and the radius you can see here at the bottom as it's described. It is the distance between the axis of revolution and the graph of f of x or g of y. So let's do an example so you can see how this will work for us. We have an equation that's y equals 9 minus x squared, and if we were to manipulate this a little bit, you would very quickly find out that this is actually a semicircle graph. And it has a radius from that 9 of 3. And so we go from 3 to negative 3 in all directions. But we were actually told that we were only supposed to go to 2 in this particular problem, because it says it wants me to go from negative 2 to 2, meaning that my shaded area right here is what we're going to be considering. Now, because this is a circle, it has a very, very nice feature that it's symmetric. So we could, instead of considering my area going from negative 2 to 2, we could do the area from 0 to 2 and then just double it. So let me write down our formula of where we're starting here. So this is actually my area formula, S equals, and we have 2 pi times the integral, and I'll write it out officially the way it looks like right here, negative 2 to 2. Now, what our radius is our radius is actually the length from the axis of revolution, which it said was my x-axis, up to the curve, and that of course is simply the distance y. And y is the square root of 9 minus x squared. So my equation starts out with square root of 9 minus x squared. Then I'm supposed to use the derivative of this. And we haven't taken that derivative formula yet, so let me actually move what I'm working with down a bit. And then we will get to that didn't seem to work so well. Let's try that again. Alright, we'll just take the derivative up on top. My board's not acting quite right for doing that. So one of the things you might want to recognize right at the beginning is that it might be helpful to think about this as 9 minus x squared to the 1/2. So as with always, the derivative, this is a chain rule right here, and so we're going to take our derivative by taking our 1/2 down. We rewrite the inside to 1 degree less, or 1 power less than the degree, which is negative 1/2, and then the derivative of the inside itself, which is negative 2x. So the 2's, of course, will cancel. I still left it with a negative, so I have negative x, and I can deal with the negative exponent as being in the denominator, and the fact that the 1/2 is a square root. So this is 9 minus x squared underneath the square root of the denominator. So over here in this equation I have the square root of 1 plus, and then we're having the negative x over the square root of 9 minus x squared, all of that squared dx. Alrighty, so I mentioned this just a moment ago, but what I'm going to do here is I'm actually going to double the amount of the area. So I'm going to double this to be 4 pi, and I'm going to shorten my length of my area to go from 0 to 2, and again this only works because of the symmetry that's involved. Now on the other portion of this, that is the actual equation portion, some lovely things happen right at the get-go. So we've got that first square root there, and then we've got the square root of 1, And when I square what's in parentheses, I get x squared over 9 minus x squared, which means I could actually combine that with the 1 at the very beginning of that square root. So this is 4 pi times the integral from 0 to 2. And I can make my denominators the same, so this right here will be 9 minus x squared over 9 minus x squared. So first of all, this didn't change. This is the square root of 9 minus x squared. And then we have the square root of 9 minus x squared plus x squared over 9 minus x squared dx. So hopefully in looking at this point you see some similarities. I have a square root 9 minus x squared on top and on bottom. So I actually end up with, this is 0 to 2. I have the square root of 9 minus x squared. And then we'll cancel these in a moment. This is a square root of 9 minus x squared in case you hadn't sort of seen what my verbiage was telling me. And then on top I have the square root of simply 9. So this is going to be in, this is our area, and this is going to be the 4 pi times the interval from 0 to 2. And we want to simplify this expression. So as you can tell clearly that these cancel out, and the square root of 9 is simply 3. Let's try that again. There we go. So my antiderivative over here I'm going to be taking is just the antiderivative of 3, which I love. I mean, that makes the derivative so much easier. So we have 3, we have to take our antiderivative of 3, which is 3x, and evaluate that at 2 down to 0. So I have 4, well, I might as well multiply it. So this is 12 pi times 2 minus 12 pi times 0. And if you think of it that way, or a couple others probably, we can actually say that this is 24